Download this code from codegive.com, link in the description below. Pastebin keyless, a comprehensive guide to secure secret management in etc. This tutorial will delve into the world of Pastebin keyless within the etc. Ethereum Classic ecosystem. We'll explore the concept, the reasons behind its usage, the technical implementation with code examples, Solidity and Web3.js, and discuss security considerations. What is Pastebin keyless? Pastebin keyless is a pattern used in blockchain development, particularly in etc., to manage and distribute sensitive data, such as API keys, connection strings, and other secrets, securely without hard-coding them directly into smart contracts or client-side applications. It leverages decentralized storage and cryptographic principles to enhance security and accessibility. The name derives from the idea of using something akin to a Pastebin, though not literally pastebin.com, for secret storage, but with mechanisms to grant access based on blockchain identity and permissions. Why use Pastebin keyless in etc.? 1. Security asterisk. Avoid hard-coding secrets. Hard-coding secrets directly into smart contracts is a massive security risk. If the contract is compromised, example through a vulnerability or upgrade, the secrets are exposed. Pastebin keyless keeps secrets separate from the contract code. Decentralized access control. Instead of relying on centralized authentication, access control is managed by the blockchain and based on Ethereum addresses or other on-chain verifiable attributes. Key rotation. Secrets can be updated, rotated, without needing to redeploy the smart contract, which can be expensive and disrupt the application. 2. Maintainability. Centralized secret management. Manage secrets in a central, auditable location, simplifying updates and revocation of access. Reduce deployment risk. Avoid redeploying smart contracts just to update secrets. 3. Flexibility. Dynamic secrets. The system can potentially support dynamic secrets that change based on blockchain state. Fine-grained access control. Grant access to specific contracts or addresses. Off-chain computation. Utilize secrets within off-chain applications that interact with the blockchain, without storing the secrets on the blockchain itself. How Pastebin keyless works, a step-by-step explanation. The core idea revolves around these principles. 1. Secret storage, off-chain but secure. Secrets are not directly stored on the blockchain in plain text. Instead, they are encrypted. The encrypted secrets are stored in decentralized storage like IPFS, Swarm, or a more bespoke solution using a database or file system, encrypted with a key only accessible by authorized entities. 2. Smart contract for access control. A smart contract acts as a gatekeeper. It defines the rules for who can decrypt and access the secrets. It stores crucial metadata, such as the location, IPFS hash, swarm address, etc., of the encrypted secret, the encryption algorithm used, and access control lists, ACLs. 3. Encryption and decryption. Secrets are encrypted before being stored using a robust encryption algorithm, example AES 256. Decryption is performed off-chain, typically within a client-side application or a backend service. The decryption key is derived from the user's Ethereum address and potentially other contextual data, example current block number, contract address. 4. Permissioned access. The smart contract holds the list of addresses authorized to access the secret. When a user wants to access the secret, their address is checked against this list. Asterisk the smart contract may also implement more complex access control logic, such as role-based access control, RBAC. Example implementation, a simplified Pastebin keyless. We'll create a simplified example for illustrative purposes. This example uses IPFS for storing encrypted secrets, a basic AES encryption/decryption library, and a simple smart contract for access control. 1. Solidity Smart Contract, secretkeeper.sol. Explanation of the Solidity code asterisk. Ownable inherits from OpenZeppelin's ownable contract, providing basic ownership and admin privileges. Secret info struct defines the structure for storing secret metadata, IPS hash, encryption algo, and active status. Secrets mapping maps a hash of the secret name to its secret info. Hashing prevents exposing the secret name directly. Authorized addresses mapping stores a list of addresses authorized to retrieve secret information. Adds secret function adds a new secrets metadata to the secrets mapping. Only the owner can add secrets. Update secret function updates an existing secrets metadata. Only the owner can update. Deactivate secret function deactivates a secret, preventing access. Only the owner can deactivate. Authorize address function authorizes an address to access secret information. Only the owner can authorize. Unauthorized address function revokes authorization from an address. Only the owner can unauthorize. Get secret info function retrieves the secret's metadata, IPFS hash and encryption algorithm. This function is the entry point for authorized users. It returns the IPFS hash and the encryption algorithm, so the client can then retrieve the encrypted secret from IPFS and decrypt it. Only authorized modifier restricts access to functions to authorized addresses and the owner. Events the contract emits events to track key actions, making the system auditable. 2. Off-chain secret encryption and storage, node.js/web3.js. Explanation of the node.js code asterisk. 1. Dependencies asterisk uses Web3, crypto, IPS HTTP client, and Ethers libraries. Install them using npm install Web3 crypto IPS HTTP client Ethers. 2. Configuration asterisk. Replace RPC URL with the URL of your Ethereum Classic node. Replace privat key with the private key of an account that has permission to add secrets to the contract, ideally, the owner. Protect this private key securely, use environment variables. Replace contract address with the address of your deployed secret keeper contract. Replace secret name with a unique name for your secret. 3. Encrypt and store secret function generates a random AES-256 encryption key and initialization vector. 4. In a production environment, deriving the encryption key from the user's Ethereum address or a deterministic secret phrase is crucial. Storing random keys is not secure. Encrypts the secret using AES-256 CBC. Includes the 4 in the encrypted data for proper decryption. Stores the encrypted secret on IPFS. Returns the IPFS hash and encryption algorithm. 4. Add secret to contract function creates a Web3 contract instance using the ABI of your secret keeper contract and the contract address. Calls the add secret function on the contract, passing the IPFS hash and encryption algorithm. Waits for the transaction to be mined. 5. Main function sets the secret value. Asterisk calls encrypt and store secret to encrypt and store the secret on IPFS. Asterisk calls add secret to contract to store the secret's metadata in the smart contract. 3. Off-chain secret decryption, node.js/web3.js. Explanation of the decryption code asterisk. 1. Configuration asterisk similar to the encryption code, you need to configure the etc. node URL, contract address, IPFS endpoint, and the secret name. Important asterisk set the user address to a test account that has access to the secret via authorized addresses mapping in the smart contract. You'll need to call authorize address in the smart contract using the owner account. 2. Retrieve and decrypt secret function asterisk. Asterisk creates a Web3 contract instance. Asterisk calls the getSecretInfo function on the contract to retrieve the IPFS hash and encryption algorithm. Asterisk retrieves the encrypted secret from IPFS using the IPFS hash. Asterisk splits the encrypted secret string into 4 and encrypted text parts. Asterisk crucially, it simulates deriving the encryption key from the user's Ethereum address. This is where you would implement the key derivation logic. Do not hardcode the encryption key. Asterisk decrypts the secret using AES-256 CBC and the derived key and 4. Asterisk prints the decrypted secret. Key derivation, the most important security consideration. The security of Pastebin keyless hinges on the proper implementation of key derivation. The encryption key must be derived from something unique and tied to the user, the contract, and potentially other contextual information. Example key derivation, illustrative. Important considerations for key derivation asterisk. Asterisk user's Ethereum address asterisk include the user's Ethereum address in the derivation process. This ensures that only the intended user can decrypt the secret. Asterisk contract address asterisk include the contract address. This binds the secret to the specific contract and prevents it from being used in other contracts. Asterisk salt asterisk add a random salt to the key derivation function. Salts prevent precomputation attacks, rainbow table attacks, where an attacker precomputes the output of the key derivation function for a large number of possible inputs. The salt should be long and securely stored. Consider storing it on the smart contract itself. Asterisk key stretching asterisk use a key stretching algorithm, example PBKDF2, BCRYPT, SCRYPT, to make the key derivation process more computationally expensive. This makes it harder for attackers to brute force the key even if they know some of the input data. Steps to run the example asterisk. 1. Install dependencies asterisk npm install web3 crypto ips http client at openzeppelin/contracts ethers.js sha3.dotenv. 2. Compile the solidity contract asterisk use remix IDE or truffle to compile secretkeeper.sol. You'll need the ABI, application binary interface, of the compiled contract. Save the ABI to a file called secretkeeper.json. 3. Deploy the smart contract asterisk deploy the compiled contract to your etc. testnet, example Morton, Kati, or a local Ganesha instance. 4. Configure environment variables asterisk create a .env file and set the following variables. 5. Run the encryption and storage script asterisk execute the encrypt.js script, node encrypt.js. This will encrypt your secret, store it on IPFS, and add the metadata to the smart contract. 6. Authorize the user asterisk use a tool like Remix or a custom script to call the authorize address function in your deployed secret keeper contract, authorizing the user underscore address specified in your .env file. You must use the private underscore key account, owner of the contract, to do this. 7. Run the decryption script asterisk execute the decrypt.js script, node decrypt.js. This will retrieve the secret metadata from the contract, download the encrypted secret from IPFS, and attempt to decrypt it. Remember to replace the placeholder key derivation logic with a secure implementation. Security considerations in detail ***. Key management ***, the most critical aspect. Never hardcode encryption keys. Derive them deterministically from user-specific information and other factors. Use a strong key stretching algorithm. Access control ***. The smart contract's access control mechanisms are essential. Implement robust authorization logic to prevent unauthorized access to the secrets. Consider role-based access control, RBAC, for more complex permissioning. Data integrity ***. Use cryptographic hashes to verify the integrity of the encrypted data retrieved from IPFS. Store the hash of the encrypted data in the smart contract along with the IPFS hash. Compare this hash with the hash of the downloaded data before decryption. Encryption algorithm ***. Use a strong and up-to-date encryption algorithm, example AES 256, CHA 20 Poly 1305. Avoid deprecated algorithms. Confidentiality of metadata ***. While the secret itself is encrypted, the IPFS hash and encryption algorithm are stored in the smart contract and are publicly visible. Consider whether this is acceptable for your use case. IPFS pinning ***. If you are using IPFS, ensure that the encrypted secret is pinned to at least one reliable IPFS node to prevent it from being garbage collected. Consider using a pinning service. Side channel attacks ***. Be aware of potential side channel attacks on the key derivation and decryption processes. Minimize the time it takes to perform these operations. Auditability ***. The smart contract should emit events for all key actions, such as adding secrets, updating secrets, and authorizing addresses. This makes the system auditable. Alternatives to IPFS ***. Swarm ***. Another decentralized storage platform. Centralized database. With encryption you could use a centralized database to store the encrypted secrets, but this reduces decentralization and introduces a single point of failure. However, it may be more practical for certain use cases. Ensure that the database is properly secured. Cloud storage, with encryption similar to a centralized database, but using cloud storage services like AWS S3 or Google Cloud Storage. Encryption is crucial. Conclusion Pastebin keyless is a valuable pattern for managing secrets securely in the Ethereum Classic ecosystem. By storing encrypted secrets off-chain and using a smart contract for access control, you can avoid hard-coding secrets in your contracts and enhance the security and maintainability of your applications. Remember that the security of this pattern depends heavily on the correct implementation of key derivation. Prioritize secure key management practices and carefully consider the security implications of your implementation. This tutorial provides a foundation, but you should thoroughly research and adapt it to your specific security requirements and use case. Always thoroughly test and audit your code before deploying to a production environment. Remember to consult with security experts for more complex and critical applications.